All right, so chapter 11, weak acid, strong base is what that should say, or a strong base, weak acid titration, okay? Titration is just the technique of performing an acid-base neutralization reaction. So pretty much this is us mixing an acid and a base where one of them is weak and the other one is strong. That's what this whole thing is about. So here we go. This is a pretty long problem. It's probably going to take me a little while to get through this video. I'll probably go faster towards the end because we're going to end up doing the same thing over and over and over again, just at different points of the titration. So let's go ahead and start off. Look at, we've got CH3COOH. That is a weak acid right here. Weak acid. Okay. And sodium hydroxide, that is a strong base. So major species. CH3COOH, weak acid, sodium hydroxide, strong base. Okay, now the first part A, asks you to determine the initial pH. That means the pH before you've titrated anything. So inside the flask we have the acetic acid sitting in there, and then we will be adding sodium hydroxide to it by titrating it. So right at the beginning all you have is acetic acid. So the reaction, it isn't really a reaction. It is a weak acid sitting by itself in a container at equilibrium with its ions. So really this part is a weak acid problem. Okay, so there's my quote-unquote reaction, even though it's not really a reaction yet. It's just the weak acid sitting in the flask. Okay, so the next thing we do, I should have set up an equilibrium expression, which I didn't. I will in a minute. So I'm going to set up my ice chart. If all that is in there is the weak acid, this is a pretty I shouldn't say basic. This is a pretty general problem for a weak acid. You start off with 0.1 molar, 0, 0. You gain X. Again, excuse me. Again, this is really right now, this is a weak acid problem. This isn't even a titration problem yet. So what is it? It's products over reactants. So X squared over 0.100 minus X. We're going to assume X is small. Products over reactants equals K, and the K was given as 1.76 times 10 to the negative fifth. Okay, you multiply both sides by 0.1, take the square root, and X comes out to be, let's see, I calculated it out ahead of time. It is 133 molar. Well, X is your hydrogen ion concentration. So now that we know our hydrogen ion concentration, we can find pH. pH equals opposite the log of H, and H is 0.00133 molar. So you get the pH, and the pH comes out to be 2.876. This is our initial pH before any base has been added to the flask. Okay, 3 sig figs are these 8, 7, and 6 after the decimal because this 0.1 molar was 3 sig figs. All right, next. Excuse me while I open my next one. All right. The next one asks you to calculate the pH after you've actually added some base. So some of the titrant has been added. So again, we've got acetic acid. We have, which is a weak acid, and we have sodium hydroxide, which is a strong base. So this is an actual chemical reaction. Now, acid. Ooh. Remember, you keep the weak substance intact. The base, because it's strong, is legitimately OH minus, salt, and water. So this would be sodium hydroxide, sodium acetate. I don't care about the sodiums, they're spectator ions. Okay, so this is neutralization. It's a one-way arrow. This is a true chemical reaction. Okay, I forgot a step. I'm going to need you to do the dilution, because if you take two solutions and you mix them together, you cause dilution to happen. So you do M1V1, M2V2 for the acid and for the base. So molarity of the acid is 0.1. Volume of the acid is 25. New molarity, X, M2. V2, 25 plus 10 is 35 milliliters. That will give you the molarity of the acid, which comes out to be 0.0714. Okay, then you do this again, but for the base, 0.1 molar for the base. We are adding 10 milliliters of the base. New molarity, X. Final volume, 35. And the molarity of the base is 0.0286. So what I'm going to do is I'm going to set up an ice chart. And I'm going to show that this is a limiting reactant problem. I have amounts of both reactants present. So ICE. So this is 0.0714. This is 0.0286. Nothing, and remember water's a liquid, so we don't really care about it. So these are a 1-to-1 ratio, right? So you have less base, so you lose all of the base. Oops, excuse me. And you lose all of the same exact amount here because they're reacting in a 1-to-1 ratio. So you have no base left, and it looks like 0.0428 here, and this is plus 0.02, whoa, excuse me, 0.0268, so 0.0268. Okay, now one way we are taught to find pH is opposite the log of H. Well, that's kind of a problem because I don't have H plus right now. Okay, another way we can find pH is if you know POH. So POH is opposite the log of OH, and then you take that number and subtract from 14, and you could get pH, but I don't have OH either. Okay, so you have two options right now. I'm going to show you the preferred way. There is another equation on your equation sheet. It's called the Henderson-Hasselbalch equation. pH equals pKa plus the log of any conjugate over the weak substance. Okay? So if you've noticed, I have the weak acid right here, and then I have its conjugate right here. This is plug and chug. This equation, as I showed you in class, was derived from the Ka expression. I don't need you to know how to derive it. I just need you to know how to use it. So pH equals, what does the P mean again? It means opposite log of Ka. So opposite log of 1.76 times 10 to the negative fifth plus the log of the conjugate goes on top, 0.0268 and 0.0428. And you plug all of this in your calculator. I'm going to go up here. Your pH ends up coming out to be 4.579. So jumped up a little upon the addition of some base, which makes sense. Okay. All right, we're moving on. All right, part C. I'm asking you to tell me what the pH of the solution is after you've added 12.5 milliliters of the titrant, aka the sodium hydroxide. So I've kind of gotten rid of the steps because we're doing the same thing over and over and over again. So we are adding acetic acid, weak acid, with strong sodium hydroxide to get salt and water. Okay, you need to do the dilution. Again, I'm going to do it up here. It's 0.1 molar acid, 25 milliliters, excuse me, equals new molarity. What is the new volume? Well, 25 milliliters of acid plus 12.5 milliliters of base is 37.5 milliliters of acid. Okay, then you do this again, but for the base. So the base is 0.1 molar. You're using 12.5 milliliters of it. Our final volume is 37.5. That will give you the molarity of the base after the dilution. Okay, so ICE. Again, it's a limiting reactant problem. The acid is 0.0667, and this is 0.0333, blah, blah, blah. Nothing liquid, don't care. So, okay, you look at these, 1-to-1 mole ratio. This guy is less, so you're going to lose all of it. And because they're reacting in a 1-to-1 ratio, lose that same amount there. And you would gain, also a 1-to-1 ratio, the same amount here. Okay, questions? Oh, can't ask questions. My bad. So, look at a weak substance in the presence of its conjugate allows me to use Henderson-Hasselbalch equation. pH equals pKa, excuse me, that's plus the log of the conjugate, which is 0.0333, over the weak, which is also 0.0333. Well, this is 1. The log of 1 is 0. So really, pH equals pKa. So pH equals opposite the log of Ka, which is 1.76 times 10 to the negative 5th. All right, so what does pH equal? At this point, the pH equals, I got 4.754. And I told you that this is a very, very, very special point of this titration. It's called the half equivalence volume. Okay, so look at, we started off both 0.1 molar acid, 0.1 molar base, same concentration. So if you had 25 milliliters of acid, 25 milliliters of base is where our equivalence point should be. 12.5 milliliters of base is half of that, okay? Half of the equivalence volume. Well, half of the equivalence volume will always be pH equals pKa. Always, for any weak, strong titration, whether it's weak acid, strong base, or weak base, strong acid, pH equals pKa at this point. All right, moving on. We are now doing, I'm going to change colors, I'm bored. 25 milliliters, okay? So 25 milliliters is our equivalence point. This is the harder of all of the parts. So here we go. Let's see, acetic acid reacting with sodium hydroxide makes salt and water. All right. I'm going to do the dilutions up here. So it's 0.1 molar acid. You're using 25 milliliters of it. The new molarity. At this point, 25 milliliters of acid, 25 milliliters of base is 50 milliliters of solution. Okay, there's your acid. The base is 0.1 molar. You are using 25 milliliters of it. Final volume, 50. Well, right there you should see that these numbers are going to come out to be identical. You just set up the same exact dilution for both of them. So let me turn to my page and I will set up my ice chart, ICE. This is 0.0500. This is 0.0500. Nothing initially and water's liquid. So my acid and my base at the equivalence point are in equivalent amounts. That's why it's the equivalence point. That means at the equivalence point, you should have no acid and no base. All you should have are salt. I will gain that right here. And water. Okay? So here's the issue. The issue is if you want to calculate the pH, all you have it to calculate it based off of is salt and water. And so there's a, okay, what's the first way to calculate pH? pH equals opposite the log of H. I don't see H plus anywhere, so I can't use that one, okay? So what's the next easiest one? POH. POH is opposite the log of OH. 14 minus that number is pH, but I don't have OH either, okay? What we have been using is this equation. pH equals pKa plus the log of A conjugate over week. Okay? Now, the problem is in this part of your titration, here's your conjugate right here, the acetate. I don't have any of the weak. You cannot use this to calculate pH if you don't have both the weak substance and its conjugate. This is out. You cannot use Henderson-Hasselbalch. So here's something special about the equivalence point for weak, strong titrations. The pH is based on the salt that is there, okay? And the salt is this guy, because all that is in there is salt and water. Now, when this was strong, we said pH was 7. But because this is a weak strong, it's not that simple. This is going to be called hydrolysis of the salt. So here's what happens. We take the salt, which is present with water, and remember this salt came from a weak acid, so I'm going to do this to equilibrium, okay? This guy, weak acid, so this is a conjugate base. So this guy's going to act like a base. Well, what do bases do? They are hydrogen ion acceptors. So you get acetic acid back. So this guy takes a hydrogen, and so that means the water loses the hydrogen. So you're left with OH minus here. Okay, let's set up an ICE. I'm getting really good with the different colors. I'm pretty impressed with myself right now, if I say so. Okay, so I know how much of the salt that I have. I have 0.0500 molar. Water's a liquid, we don't care. 0, 0. There is no weak and no base initially, right? Because they got neutralized. That's the point of being at the equivalence point. So what we have to do now is what we've always done before. Let X equal something. So I'm going to let it equal hydroxide, let's say. They're a 1-to-1 ratio, so this is X. This is minus X, so this is 0.0500 minus X. And then you set up your equilibrium expression, products over reactants raised to their coefficients. So we've got X squared over 0.0500 minus X equals, be very careful. So this is what I showed you in class. This guy is a base. So when you set up this expression, it needs to be for a base. Ka is what was given. So right over here, if you look up this fancy equation, this is a way to convert at any moment between a Ka or a Kb. So plug your Ka, this guy in, right here. Rearrange, divide both sides by Ka. I'm going to let you do this. I'm not going to do this for you. And you'll be able to get the Kb, which comes out to be 5.68 times, is this right? I feel like it was 10 to the negative 10, but now I am going to double check in my calculator. 1.0. Are you checking with me? Yes. Okay, 5.68 times 10 to the negative 10. Okay? So again, Kb, because this is a base. This is a basic salt, which we'll get more into later. So remember, we always assume X is small. Multiply by multiply by both sides, 0.05. Square root X comes out to be 5 point something, 3 something times 10 to the negative 6 molar. Well, that's great because X is OH minus. So I'm sorry I'm running out of room and I don't have more space for this problem. So POH is opposite the log of 5.3 times 10 to the negative 6 because that's OH. So it looks like I got my POH to be 5.276. And you take this number, you subtract from 14, and my pH is 8.724. Notice at the equivalence point for this titration, our pH is not 7, it is 8. It is a basic pH because this is a weak acid and a strong base titration. That strong base is what causes our equivalence point to be at a basic pH. Okay, again, this was the very hard part. Understanding that all you have at the equivalence point is salt and water, and because this salt is basic, we have to, it undergoes hydrolysis with water to cause all of this to happen. Okay, so the last part is actually not too bad. At this point, we're going to be past the equivalence point, so at 35 milliliters. So here we go, CH3COOH, acetic acid, strong base, salt, water, okay, ICE. All right, did you do the dilution? Because you're so ahead of me. Here's the acid, 0.1 molar. We're using 25 milliliters of it. New molarity after the dilution. Well, after the dilution, we have 35 milliliters of base and 25 milliliters of acid, so that's 60 milliliters of stuff. That's what you would do for your acid. All right, the base is 0.1 molar. We're using 35 milliliters of it, and new volume 60. So the acetic acid, it looks like it comes out to be 0.0417, and the base comes out to be 0.0583, and nothing here, and water's a liquid. So in this instance, we have the weak acid that is limiting. So we've already run out of acid at this point, and the base is in excess. So you lose all of the acid, and again, everything is a 1-to-1 ratio. So that makes all of this really nice. Nothing here, 0.0417 here, and this comes out to be 0.0166, blah, blah, blah. Okay? Now, you have the weak substance and its conjugate right here, which would allow us to use Henderson-Hasselbalch, but we don't have any of the weak substance, so Henderson-Hasselbalch equation is out. What's really awesome is we have excess hydroxide. Find POH. It's perfect, opposite the log of OH, which is 0.0166. So POH equals 1.778, and pH equals 12.222. So a fairly basic ending, well, I guess not ending, but after this point, pH, okay? And then I had you go ahead and draw your titration curve. I'm not going to really draw it in great detail. It usually starts, so if this is pH 7, usually starts a little higher than normal when it's a weak acid. Equivalence point is always above 7. Okay, you ended very basic, so this was like maybe 12, 13, and right, our equivalence volume was 25. Our half equivalence volume, which was 12.5, this is where pH equals pKa. It's a special point, okay, right here. And as I sort of pointed out in class today, this whole region right here, this whole region is a buffer region. This happens in weak, strong titrations. The beginning forms a buffer solution, which is why the Henderson-Hasselbalch equation is actually known as the buffer equation. The neutralization process, in turn, forms a buffer at the very beginning of this reaction, and that's why we get to use the buffer equation for this part of the titration. So that is how you do a weak acid, strong base titration. It would be done very similarly. You would just be starting off at a different point with a strong base, weak acid titration. Again, you have to be able to do at any point of a titration curve. All right.